Hey Royals, in today's lesson, we're going to look at a concept called weightlessness. And this often gets misused in movies and TV shows. In fact, it assumes that there is a point when we can turn off gravity and we essentially just float. And this is never the case. Gravity, we can't just simply turn on and off. Okay, so we'll try to kind of look at that concept a bit further today. And so for that, we're going to look at several different scenarios of Captain Royal in an elevator. In one case, he will be standing in an elevator that's moving at a constant velocity, meaning the acceleration is 0. And then in the remaining 3 cases, he's going to be in an elevator that is accelerating. In one case, it will be accelerating up, and then 2 cases, it will be accelerating downwards. Okay, so to help us out with this, we want to determine what would the scale, the bathroom scale, measure as his weight in each of these figures. And what the bathroom scale is actually measuring is our normal force. And so for that, let's take a peek at how to calculate his normal force inside that elevator. So if we draw a free body diagram of Captain Royal, let's go ahead, here's his box, and I say that there's a force of gravity acting downwards on him, we'll say Fg. And there's a normal force acting upwards on him because he is in contact with the floor of our elevator. We'll say that it is Fn. Now, using Newton's second law, we can say that the net force acting on Captain Royal is equal to his mass multiplied by the acceleration. And the net force and the acceleration are both vectors, so we should put the arrows above them. Working out the net force, we'll see that we have the net force as a vector plus the gravity force as a vector is equal to the mass multiplied by that acceleration. So let's isolate for Fn. Fn as a vector is equal to our mass times the acceleration, subtract off that weight force, that force of gravity. And we learned in an earlier lesson that that force of gravity can be represented as the mass multiplied by the gravitational field intensity as a vector. So if we work this through a bit more, we notice that both terms on our right side of our equation have a mass component, so we can factor it out and say that it's going to be the difference between that acceleration vector and the gravitational field intensity vector. Okay, so we'll use this equation right here as our representation of the normal force. And so I'll slide back up to our example here, and I'll write that formula one more time. It says that the normal force is equal to the mass multiplied by the acceleration vector subtracting the gravitational field intensity vector. Okay, so we'll use this to determine the net force acting on Captain Royal in each of the cases. So I'll do the first one with us. So Fn is equal to m, and then the difference between the a and the g. And we'll say that that's equal to 60 kilograms multiplied by 9.8 meters per second squared. Sorry, in this case, there is no acceleration. So 0 meters per second squared, subtract 9.8 meters per second squared downwards. Okay, so I have here that it's going to be 60 kilograms multiplied by negative 9.8 meters per second squared downwards, and when we multiply that through, we get a value of 588 newtons, and because it becomes negative and I have it downwards, I will switch it to be upwards. So that tells me that the normal force acting on Captain Royal, if he's standing in an elevator that is moving at a constant velocity, is going to be 588. Now, what I want you to do is I want you to repeat this calculation for an acceleration that is not 0. So we have an acceleration that is 2 meters a second squared down, one that's 2 meters a second squared up, and then let's look at that dangerous case where the elevator's cable snapped and Captain Royal is accelerating downwards at 9.8 meters per second. So I'm going to encourage you, pause the video, try these 3 calculations for yourself, then come on back and check your answers with mine. So welcome back. What you may have noticed is when the elevator is accelerating downwards with you, you appear to be weighing less. So your normal force actually becomes smaller. Whereas if you were accelerating upwards, your normal force seems to be larger, which makes you feel like you are weighing more. So it appears that to you that you have a larger weight. Now, in the case where that cable snaps and you're falling downwards at 9.8 meters per second, you feel something known as apparent weightlessness. So the concept of apparent weightlessness occurs when we are accelerating downwards at 9.8 meters per second squared. So you may have experienced these types of apparent weight changes when you're on something like a roller coaster. When you're coming over the top of that hill and you're rushing towards the earth again, you feel like you're semi-floating. If you were ever on a roller coaster and the seatbelt kind of wasn't as tight as it could be, you almost lift up from your chair and you feel like you're flying a bit. But once you're at the bottom of that valley and you start coming up that next hill, you almost feel like you're being jammed into your chair and you weigh maybe twice as much. And that's the idea of apparent weight being pushed upon you. It's this G force. So you might experience 2G at the bottom of that valley on the roller coaster. Okay, so the idea when we are falling at the rate of acceleration, 9.8 meters per second squared, we feel like we are weightless. We feel like we're just floating there. And astronauts train this way. They go into airplanes that follow these parabolas in the sky, and as they rush towards the Earth, everything inside the airplane starts to accelerate at the same rate of 9.8 meters per second squared. So that makes you feel like you are weightless. Okay, so that's the idea of weightlessness. And it really is just an acceleration due to gravity. So if you have any questions about this lesson, please reach out to me or bring your questions to class.